Okay, so now the record is on. Ladies and gentlemen, today we will begin the last topic of our class. That is something that, well, I'd say maybe some of you will get to use it. You know, it's still the tools that engineers use to deal with this kind of problem. And the problem, let's say it's not a problem, it's part and parcel of engineering, civil engineering life. That is the stuff that we call moving loads, okay? Moving loads. Some kind of the load that can certainly move, okay? So when the load moves, it can cause our, we can call this design function, okay? Design function, but when you are going to design your structure, let's say a beam, you must consider the shear and the moment, and sometimes also the reaction, which is, you can view that as a shear. But these are called design function. So when the load doesn't stand still, it causes these values to change, right? So we are going to have to deal with these moving loads. For those who design something that contains such load, okay? So, well, without further ado, we can see a lot of moving loads in everyday life. For example, this is crane, right? And you see that part will move, you know, up and down the boom, okay? This is also part of the crane, but if it has two legs like this, and it's big, and they will call that a gantry, okay? This is also a crane that we use the puller system to help reduce the force that we need to apply in order to lift the load. We have a moving crane like this in our department, right, to move things around in our structural lab. So this beam has a moving load in this direction, you see, and the beam itself also moves in this direction. So it's moving load all the time. And also in the factory where you need to move stuff along the way, we would not use the manpower to carry the load because that's inefficient. So we use this kind of instrument to help us, okay? And yep, this is a gantry. You see how big it is? I'm trying to find the size of human being around in the picture. That's a human being, right? See how big it is? So this is the instrument that we call gantry. Yeah, that's the word, gantry. We use it to move the containers around the port area, of course, much more efficient than the trucks and the forklift or things like that, okay? Now, and yep, this, you can see this, right? If you come to the campus by way of the expressway, because they are now constructing another bridge alongside the existing Rama 9 bridge, and they use something like this called the launching truss, okay? And this is the sort of a diagram, how it works, okay? It will launch the red one, you see, and when the blue one is here, that is a segment of the precast concrete that has been constructed somewhere, you know, in a very wide area, and it has been transported mostly by water to the site, and just put on the launching truss and launch it. And once this segment is complete, you know, the red one stays there, the blue one moves here, and then the red one moves further, and then now we continue another process there. So everything moves. We call that a moving load. Another one is, yeah, that's a moving load, okay? Launching truss. Of course, the classic one, cars, right? Cars move. So cars are essentially the moving load acting on the structure that support the bridge or, you know, the road and so and so. So many of you will get to work in the highway business, you know, the bridge business. And of course, you have to know what the influence the moving load has on your structure. And incidentally, the tools that we use to monitor the moving load or analyze the moving load is called the influence line, just to see how much influence the moving load can affect your structure. Okay, because the load moves, it means that load moves, it means the change of locations of the load, right? Or another word that you can keep in mind is we call placement. Okay, how the load is placed on your structure. And so therefore, if the location of the load changes, the placement changes, the maximum internal force will change accordingly. All right. And you will be introduced to the new tool for you that civil engineers nowadays to use to design the structure that has to carry the moving load. We call this the influence line. Okay. Keep in mind that the influence line is not a shear force diagram or bending moment diagram. Okay. It's the line or the graph, you can say, that shows how much your design function changes when the load is placed in different locations on your structure. Okay. So without further ado, you guys please open up this document. Okay, and we are going to take a look at example number 25. Do you have that already?
Yes.
Okay, good. So this is the beam, okay, with the load P that moves all over the place. So let us begin by taking a look at the beam and see how the reaction changes if I move the load around. Okay, so first, same beam. And let's call this, say, point A and point B. Incidentally, I think it's the best options for the names, okay? So let's say, first, if my load P is here, okay, we are beginning to move the load around. So let's begin from the leftmost side of the beam. The load P is now on the support. What would be your reaction today? I think without further ado, you should know that your RA is now equal to P, right? And RB will, well, if RA is equal to P, RB will be equal to 0, right? It's pronounced like French, 0, okay? So now, any question on this? Pretty straightforward, I suppose. Now, no, right. Thank you for your response. I think the atmosphere is a little bit, say, more welcoming than being on campus somewhat, or I'm used to it. I don't know. So, okay, anyway, let's move this. I can make it straight, why don't I? I kind of prefer the line that is not naturally straight. It feels, I can feel the handwriting, so to speak. But anyway, now let us move the load P out a little bit. And let me say this distance is 0.1 L. We move the load 10% of the span length. Okay. Remember the span length is L. So now I hope that you don't have to take moment every time you calculate the reaction, right? But if you have to do so, do it. But now quickly, if that's 0.1, that's 0.9, right? Take moment at B, it's a 0.9 P divided by L. So RA is now 0.9 P, right? You see, the load moves, the reaction changes. And now you have RB. RB will be equal to 0.1 P, right? Again, we will continue to move this stuff. Let's say P now moves to the location at the length equal to 0.2 L. That's P. So similarly, you can take moment, or you can just look at the big picture and tell me right away that RA is now going to be 0.8 P, and RB is now 0.2 P, right? You see the load P now begins to move a little bit further away from the support, and so RA continue to reduce in magnitude, while RB continue to increase in magnitude. And we can keep doing this, okay? Let's say now we are at midspan. If P at midspan, say this, midspan is 0.5 L, right? You now see RA is 0.5 P and RB is also 0.5 P. However, if I continue to move on, right. I'm caught between the fact that I should write everything in the same page or just continue downward. Let's keep it in the same page, maybe better. Okay. So now P move past midspan. So let's say I reach this point and try to make the same kind of information where the distance to the support B is now 0.2 L. Okay, so that means this is 0.8 L, right? Now A will be reduced to just 0.2 P, right? D is now approaching the full P. Because when I keep moving this, say up now, and P reaches this distance, which is now only 0.1 L to the right support, you can guess now that this RA is down to just 0.1 P, and RB is now 0.9 P. And the last one, of course, when P reaches B, maybe just for clarity, when P reaches B, now you have RB equals to P, right? Everybody can see through this, right? I think it's pretty straightforward. This shows you that when the load placement changes, your design function, in this case, the reaction changes. And if I try to plot the value of the reaction at A, okay, by using the X coordinate as the location of the load, okay. If I use my X coordinate as the location of the load and Y coordinate as the magnitude of RA itself, okay. Now you need to switch your paradigm, your perspective a little bit. Now the X is the location of the load, okay. Y becomes the size or the magnitude of your reaction at A alone. So you see from this first picture, I have Y coordinate equal to P, right? When the load is right here at L equal to 0. When the load moves to this point, which is this free body diagram, Now I have the load here equal to 0.9 P. And at the location now 0.2 L, I now have the magnitude of the load equal to 0.8 P. At midspan here, I now have 0.5 P. Okay, and move to 0.2 here, I now have 0.2 P and 0.1 P, and gradually things become zero. So I should connect all these dots, you know, and I have this line. Okay, doesn't look that beautiful, but it should send the message across. So this becomes the graph that represents the magnitude of your reaction a day. Okay, but the reaction at A, when the load is at any location on your beam. Okay, it's not the shear force diagram where it shows the shear value at each location on the beam. This shows only reaction at A when the load is at each location on the beam. So you need to change your idea a little bit. Okay. So insofar, any question? Hello?
For me, no.
No, sir.
Still crystal clear, right? Pretty piece of cake. Now I can tie my hair. It's still damp, but it's moist, but still much better now. So, okay, this is RA. So let me do the same thing, but now this time I will try to, so we are done with this. So let me move it here, okay, so that you can stay with this, these free body diagram. Cut it and move it here. All right. So now I will do the same, but instead I will focus on the reaction at B, okay? So at the zero location, you know, L equal to 0, your RB begins from 0 and gradually moves up. At the 0.1 L, it becomes 0.1 P, and then that's not 0.1 P at all. What did I write? 0.1 P. Okay, and let's connect. Okay, at the location 0.2, it becomes 0.2 P, right? And at midspan becomes 0.5 P. And when it moves towards support B itself at this location, which is 0.8 from A, it becomes 0.8 P, and until it reaches P at the end, okay? And this line looks a little bit ugly, but when we connect that, okay. So this again becomes the line that demonstrates the magnitude of RB when this load P is at each location on the B. So are we okay on this one?
Yes.
Ooh. Whoa. Anyway, right. So let's move this here so that we can now focus on the graph. All right. So this is the magnitude of RB when the load is along the beam. So generally, ladies and gentlemen, it's not very convenient to do this by saying, okay, we have the load equal to P. Instead, we will change the load from P to, can you guess?
L.
L is not load, L is a length.
Oh, okay.
But thank you for your participation. I do appreciate that. But we changed the load from P here to 1, right? So if P is equal to 1, right here, we can start saying that, okay, the magnitude of the reaction here is 1. And this becomes 0.9, 0.8, 0.5, 0.2, 0.1, and 0. This becomes 0.1, let me move that a little bit as well, 0.2, 0.5, 0.8, and 0.9 and 1. Okay, so this, ladies and gentlemen, is what we call influence line. And what you see now on the left side, this is the influence line of reaction at A. This is the influence line of the reaction at B. You see, let me repeat that again, that when you look at the influence line, it means that this magnitude is the reaction at A when the load is at the location 0.1 L from the left support. So instead of having to calculate the reactions by taking moment so and so, if you have the influence line, you can look at the line itself and be able to pick out the value of the reaction right away without having to go through the calculations like before. So that is the influence line. Okay, any question on this? Oh, quiet.
Crystal clear.
Okay, okay. So, you know, for better or worse, everyone who graduates from KMUTT, Civil Engineering Department, know this word. You go out and when you start mentioning this word, you know, oh, you guys have a class with Ghana Pinat, right? All right. Anyway, now it's a reaction. So if you are crystal clear, let us try to look at other design functions that we still need to use. That is the shear and moment. Okay. So I think it's not a bad idea to try to look at the shear and moment at midspan. Okay. So now focus and clear your mind and trust your force. Okay. We are going to place the load at each location like before. But in order for us to have the shear and moment at these locations, we now have to do little old school business called cutting the free body diagram. Okay, so from this situation, I now have to start cutting the free body diagram. So same beam, okay? Now with the load equal to 1, and I want the value of the shear and moment at midspan, remember? So I start placing the load here at 1. What would be the shear?
1.
Really?
Oh, 0.
Reaction here is 1, right? So shear is 0. And moment is incidentally 0 as well. Maybe I should use a different color. Would be helpful, I suppose. Moment is also 0. You know, I don't like purple, but somehow I think it's going to give you a clear picture. Now, let us move the load. Maybe I will try to write bigger. Okay. Now your load is here. 1. The location here is 0.1 L. So now you know the reaction from our previous endeavor, that this is 0.9, right? So now, if it's 1, it's 0.9, it means that this is going up, equal to 0.1. Correct?
Yes.
Yeah. The moment, it's kind of difficult, but let's do it. It should be positive moment. Moment is going to be equal to 0.9 multiplied by 0.5 L minus 1 multiplied by 0.4 L, right? So that's roughly maybe 0.05 L. Right? Now, move on. Next point. Chop, chop. Oops. If I placed it here at the location 0.2 L, 0.2 L, that is 1. Now the reaction is 0.8. Okay? What would be the shear? It's upward, and V is equal to 0.2 to maintain sigma Fy equal to 0, right? And the moment now is equal to 0.8 multiplied by 0.5 L as usual, minus 1 multiplied by 0.3 L. And this is 0.1 L, right? Now, let's move on to, you like me to demonstrate maybe 0.3 L for better clarity, or you okay? Can we move to midspan now?
Yes. I mean, you can move.
Yes, you want me to, right?
Yes.
Okay.
I mean, you can move to Mr. Pan.
Oh, okay, good, thanks. Seems like your opinion is everyone's opinion, so because we're kind of quiet anyway. So all right, so if we are at midspan, now the load itself is right here at midspan. So you see, it's gonna get a little tricky with the shear because the reaction is 0.5 now, we're at midspan, right? Now when you draw the shear, because right here, the unit load is now at midspan itself. So let me try to find another color. Maybe this. What would be the shear? If you are on the right side of the load, if you are on the right side of the load, you will see that your shear is going up. On the right side, right? Slightly on the right side, say 1 nanometer to the right side of your unit load. Are you still with me? Oh, wait, the one is. If we cut the free body diagram just to the right side of the load, I will draw this and then I'll erase it because it gets in the way. Okay. If the load is here and your free body diagram is slightly, just very slightly to the right, this is 1. So your shear here will be 0.5 and 0.5. Okay. But if I cut this free body diagram slightly to the left of the load, if we cut it slightly to the left, say this free body diagram falls a little short before we reach the load itself, What do you think you need to have in order to maintain equilibrium on your free body diagram? When you look at this piece, in order to have equilibrium, your force will have to be a downward of 0.5 because you haven't reached the point where the unit load is applied, right? Are you with me?
Yes.
Yes, sir.
Okay. Okay. So yeah, say and that V equal to 0.5. On the left. Okay. Now, what about moment? I will raise this one. And
Smile moment.
yeah, I know. Yeah, right.
Oh, okay.
I mean, the magnitude. The moment is going to be now 0.5 multiplied by 0.5 L. But now we take moment right where the unit load is. So that becomes our magnitude, right? So it becomes 0.25 L. Okay. Now our load will move past this. Remember that this remains our free body diagram because we need to cut this in order to show the internal shear and moment at midspan. So when the load reaches the same location here, it is, 0.2 L from the right support. Now I still have this free body diagram. I cut it at midspan, right? But now my load is here. And the location here is 0.2 L, right? So plainly speaking, the load is now outside of my free body diagram. And now I have the reaction equal to 0.2. So what would be our complete free body diagram? I now have to have the shear, right? Equal to 0.2. You can see that, right? Sigma Fy has to be equal to 0. And I still need to have moment. Still positive moment. And this moment is simply 0.2 multiplied by 0.8 L, which is oh no. Oh, nobody helped me. And it's kind of morning. It's not 0.8, right?
0.5.
Yeah, it has to be 0.5. 0.5 L. So incidentally, it becomes 0.1. Yeah. And likewise, if I continue to move the load, to the location now, only 0.1 L to the support. We have the same situation here where the shear is 0.1. Here is 0.1 down, and the moment is the positive moment equal to 0.1 L, 0.1, sorry, multiplied by 0.5 L. So that's 0.05 L. Okay, and again, everything becomes 0, just like the first picture when the load arrives at support B. Okay. So now I am going to plot the magnitude of these design functions, beginning from shear. So that's a shear, okay? Shear at midspan. Remember, this the y ordinate will show the magnitude of the shear at midspan, while the x ordinate will be the placement of the load. So when the load is here at 0, our shear is 0. When I move the load to 0.1, shear is going up equal to 0.1. But remember, your sign convention of the shear is like this. So it goes up on the right means that it is a negative shear, right? So here we go, minus 0.1. If we move on to this, we have minus 0.2. Oh, damn it. Okay. Minus 0.2 at the location 0.2 out until we reach the midspan. You see, we now have the shear in both directions. So when you reach the midspan, in fact, your shear now has both negative and positive value. And that is 0.5. And that is minus 0.5. Right? Until again, when it is at the location 0.2 from the support. Here you have the shear downward at midspan, which incidentally is a positive shear. So you can see this is going to go like this, right? And this is 0.2 and 0.1 and 0 in the end. So this is the influence line of the shear at midspan. How the value of the shear at midspan changes when we move the load around. Are you with me?
Yes.
Yes.
Hope so, right? Actually, you know, everything here, this is what we have been doing so far from statics. We just place the load and then cut the free body diagram and calculate. What we do here, you know, we just extend this knowledge slightly further by, you know, putting all this information together and create another graph that we now call the influence line. Okay, so let me just try to move this. Again, paste it here. Now, I am going to take care of the last one, which is the moment. Okay, now, at location x equal to 0, where the load is here, your moment is 0. When your load is at the location 0.1, your moment is now 0.05 L. When your load is here, location 0.2 L, the load becomes 0.1. Okay, it looks like a straight line, and when you reach the midspan, it's 0.25. So you can imagine it's going to be a straight line like this. Oops. Okay, and let me try to move this a little bit. This is 0.1 now. And right here, it's the peak. It is 0.25 L. And you can notice that things will go back to 0 again. Oops. Here is at the location 0.2 from the right support. This is 0.1. This is 0.05 L, right? So this is don't looking very beautiful, but yeah, it's the influence line of the moment at midspan. You see, the moment at midspan, it changes its magnitude when we move the load around. It produces maximum moment. The load produces the maximum moment when we incidentally place it right there at midspan and moves down when the load moves away from midspan as well. So this becomes the influence line of midspan. Okay, and maybe I should try to gather it on the same page. It's here. Oops. Okay. So far, any question? Hello?
No question, sir. I have no question, sir.
You have no question?
Yes.
Like no, say, no specks in your eyes. You can see things crystal clearly.
Clear.
Okay, excellent. All right, what about others? Do we have anything? Do we have any questions?
I think no.
I think
You think no?
Yeah.
Okay, so you can see, all right, that is the introduction of the influence line. You know, you need to change your perspective a little bit because now it's the values of one design function at one location. This is no longer, let's say, for example, this is no longer the value of the moment at each location. It's just the moment at midspan only of your beam where the load is at each location. So this is not the graph that shows moment at every location. It's just the moment at midspan when the load is at these locations. Likewise with the shear. Okay. So, right. You know, it would be quite a painful experience if we have to do this every time we want to construct the influence line, right? This is just, I try to do this every year just to try to bridge the gap between the idea of the influence line and how we can actually create it with ease. So in the next hour, okay, after we understand this, we are going to move on to qualitative influence line and the idea of the professor called Heinrich Müller-Breslau. Okay, and this guy is gonna rock your world one way or the other, hopefully in the better way. Okay, so if we don't have any question, let us stop the first session here now, and let's take a 10-minute break.
Yes.